we have seen that. Hello. Hello. 哎，好像好。Okay. So we have seen that for general matrix, right? We need certain conditions so that it can be have this eigenvalue decomposition, right? And then we went to a spatial case, right? A spatial instance, which is a Hermitian or symmetric matrix, right? So that's a spatial case, and you see that's always diagonalizable. You always can have the eigenvalue decomposition, and not only that it's unitarily diagonalizable, right? So eigenvalue are real value, and also this eigenmatrix is unitary. Okay. So then now let's further consider a spatial case, okay, which is PSD matrix, okay, which is a spatial case of Hermitian matrix. Okay, so it becomes more and more structured. You see, right? It's become more and more structured. So you expect to see a stronger properties, right, for this type of matrices. Okay, so PSD matrix, right? Definition. Okay, it's like if we have a symmetric matrix, I will use this notation. Means that it's a Hermitian, okay, and the m by m matrix. Okay, I will use this notation. Or sometimes if it's real valued, then use this S. Okay, means it's symmetric, m by m symmetric. Okay. So now A is a Hermitian, okay, matrix. Then we consider this. We say A is positive semi-definite. Okay, or simply in the PSD is positive semi-definite. Okay. If whenever you consider this quadratic form, okay, this quadratic form. Okay, this quadratic form. Okay, for any x, then this is a value, right? This is a value. Also, because A is Hermitian, you can check this is a real value, right? This will be a real value. Although this is complex, x could be complex, right? But this would be real value, right? Okay, so this will be a real number. Okay, then for this real number, is always non-negative. Okay, for all x. Okay, for all x. X is complex value. A is also Hermitian, could be complex value, but this one will be real value, will be a real number, right? Because A is Hermitian. Then you consider this quadratic form is always non-negative. Okay, always non-negative. Then this matrix called PSD. Okay, this matrix called PSD. Okay, so a stronger condition is that we say for PD, positive definite. Definite. Okay, so it says a PD. Okay, then is that this quadratic form will be strictly positive. Okay, for all x it's not zero vector. Okay, as long as x is not all zero. Okay, of course, if x is all zero, this will be zero, right? So for any x, as long as x is non-zero, okay, then this quadratic form is looking positive, then it's called positive then. Later you will see that why we define this PSD or PD matrix, because right, it's really can connect to the real number, because for real number, right, we can say it's positive, right, or negative. Okay, and later you will see that this gives us a sense that we can say a matrix is positive or negative, but it's not of, okay, not of in terms of the values, but in terms of its eigenvalue or some other properties. Okay. So any questions about this definition? Right. So if none of this is satisfied, okay, none of this is satisfied, we say A is indefinite, right? We say A is indefinite, okay, if it's not PSD or PD. Or the other way is that, right, you can define is positive semi-definite. You can also define negative semi-definite. But it's less people will say in that way, right? Because you can say this is always negative, so it's a negative semi-definite. Okay, because if A is negative semi-definite, then minus A will be positive semi-definite. Okay, so it's not that common, okay, for you to see that negative semi-definite. Okay, so it doesn't have either it's not PSD, not PD, or not negative semi-definite. Okay, then it's called indefinite. So indefinite means that you consider quadratic form, then for some x, this is non-negative. For some x, this could be non-positive. Okay, so you see some x which is positive. For some x, this gives you negative values. So that's called indefinite. Okay, indefinite. Okay, so that should be clear. Then let's see some examples where this PSD or PD matrix can appear. Okay, so first, the correlation matrix in statistics, right? If you have a y is a right, it's a random process. It's a random vector. Okay, a random vector. So each element is follows some statistics, and if you learn before them in some statistics, you know that there's a it's called y sense stationary. Okay, which means that these random variables for each element. Okay, if it's a random process, if it can be changed over time, then his second order, first order statistic, like its mean or average, is constant. And for second order statistic, like a correlation that depends on only the time difference. Okay, so I'm not sure if you know this. Anyhow, it's not. It's actually important, but not very crucial in this course. Okay. Anyhow, so for this, you can define as correlation matrix, right? That's this expectation YY Hermitian, right? So this will YY Hermitian, right? It give you it's a matrix, right? It's a matrix. You take expectation, right? You see, it's IJ's elements, right? Will be the expectation of YI and the YJ, right? Y and the YJ. right? So it's a matrix, right? Then his elements that measures how correlated of these two elements, right? Yi and Yj, okay, in the sense of statistics. Then you see this is a PSD, which is a PSD. You see Ry is PSD, right? Because you can see, if you consider his quadratic form, okay, you consider the quadratic form of this matrix, right? It is this, right? This is equal to right? And this is what this is. Absolute value square. Yeah, absolute value square. So this is expectation of this new random variable, right? And this new random variable is non-negative. So its expectation, right, will be non-negative. Right? This is true for any x. It's true for any x. So easily you see the correlation is a PSD matrix, right? It's a PSD matrix. Right? In practice, we may not be able to get this, but in practice, sometimes we approximate this expectation by averaging these samples, right? So in practice, we collect many samples of this y, okay? So it says yi. Then we may use this sample average, right? Right, sample average to approximate this in sample average, right? This expectation or in sample more it's called in sample average, right? This is sample average. Right. Right. That's what we do in practice, right? We collect many samples. We use the sample average to approximate this in sample average. And you see this sample average is also a PSD matrix, right? Quite easy. You check its quadratic form, right? It will be this average of this yi Hermitian x absolute value square, right? So it's also nothing. Okay, so this is also a PSD, right? This is PSD, also is PSD. Okay, right? Similar, the covariance matrix, right? The covariance matrix is also PSD. The covariance matrix, which is y minus its mean value, right? And take it multiply with Hermitian. So covariance matrix is also PSD. Quite easy to see. Any question here? Right. Any other examples? Right. So the other example is for the Hessian matrix. Okay, if you have a multivariate function, right? If we have a function f, okay, we have a function. Okay, it's a m-dimensional space. Its input is m-dimensional space to 1. Okay, so it's a multivariate function. Then in calculus, like we can have its gradient, right? Right, its gradient vector, which is right, it's a vector that contains this partial derivative to each entries of the x, right? That is gradient vector, right? If you consider the second order derivative, then that gives you a Hessian matrix. First of all, Hessian matrix in calculus, right? It tells you that the Hessian matrix, okay, it's an n by n matrix. It's an n by n matrix, and then ij's entry is you take the second order partial derivative to xi and the xj. Okay, i's element, j's element. And it has been shown that this is equal to the order you take the derivative with respect to xi and xj is the same. Doesn't matter. Okay. So which means that this Hessian is a symmetric matrix. Right? This is we learn in calculus. So Hessian is a symmetric matrix. Okay. So how is that related to PSD? Then if the Hessian, okay, so C is symmetric, right? But if the Hessian is PSD, with PSD, okay, then what does this give us? Okay, if it's PSD, then f is so-called convex function. So-called convex function. Okay, so if it's two-dimensional, then it's like a ball. Okay, it's very nice function, so-called convex function. But if you have taken the optimization course, then you should have heard about this, right? This is a convex function. Then in optimization theory, a very nice property for convex functions, right? Is any local minima is always global minima because it's like a ball. Okay, there's only one global minimum. Okay. So Hessian is PSD that implies the function. Very nice. Okay, it's a convex function. It's a convex function. So this is also one way to check the function is convex or not. Okay, if a function is twice differentiable, okay, so it has this Hessian matrix, twice differentiable. Then one way to check the function convex or not is simply to compute this Hessian matrix and check out its PSD or not. Okay. Right. So you see, if we have a function, have this quadratic function. Okay. So this is very common to see. Okay. It's quadratic. It's quadratic function. So you can check what is gradient. What is gradient? Right? You can check gradient will give us ax plus b 2x plus 2. Okay. You can verify this by yourself. Okay. And then its Hessian is 2a. Okay, it's Hessian. So then for this quadratic function, you see the f, if a is PSD, then f is convex. Okay, and this is the exactly I said it's like a ball. Okay. Any questions here? And in notation, sometimes it's very common to use this notation for PSD. We say if A is PSD, then we will use this notation. Okay, we'll use this notation. Grade equal to 0, but this is not equal to this. Okay. So this is a skewed inequality. Okay, then this notation means PSD. Okay, if we PD, then you see people write this. Okay, this is a PD. Okay, so this notation means A is a PSD matrix. This means A is a PD matrix. Okay. So what's a property, right, for a PSD matrix, right? Because if we want to check, right, it's not all the examples are as easy as a correlation matrix that you can easily to check its PSD or not, right? Because correlation matrix is very special, right? You look at its quadratic form, and you see its PSD or not. But not always the case, right? In general, so we need to see some properties. Okay, I need to see some properties. Okay, and so then that allow us, right, to have to be more capable, right, to identify a matrix is PSD or not. Okay, not simply from checking the quadratic form. Okay, so let's see. First, we need to define this so-called principal submatrix. So what's a principal submatrix? So if we have a matrix, right? Right. Submatrix means that it's a new matrix that you taken from this matrix A. That's called submatrix. And the principal submatrix is this dual is that you define an index set, for example, 1, 3. Okay, this is you define index set. Okay, this example is like the index set is 1 and 3. Then the principal submatrix. The principal submatrix corresponding to this index set, okay, is given by, right, here is 1 and 3. Then you simply take the intersections of these points. Okay, so the principal submatrix is that you take the elements in A that his index, okay, is involved or associated with the 1 and 3. Okay, so you see this is this phone number. Okay, so this is principal submatrix will be 1, 3, 7, 9. Okay, so it's principal submatrix. Okay, so a principal submatrix of a matrix, okay, is denoted by AI, okay, and where the I is a index set. Okay, so it's that you have an index set, and the index set, of course, is from 1, 2 to n because it's the dimension of the matrix, right? It's a submatrix of A that keeps rows and columns indicated by I. Okay. So it's described here, right? This is 1 and 3. So only keep the first row and third row, first column and third columns. Okay, so the intersection will be 1, 3, 7, 9. So it gives us this. Okay. Okay. So any questions about this? Right? If its index is only 1, then the principal submatrix is only give you a value only as 1. Okay. If the index has, because here has 2 indexes, so the submatrix 2 by 2. Okay. If the index has n element, then the submatrix will be n by n. Okay. Okay. Then the first property is that if A is PSD, then any of these principal submatrices also be PSD. Okay. If A is a PSD matrix, then any of its principal submatrices. But if this is true, then obviously we can see that, right? First is that if A is PSD, then his diagonals is non-negative, right? Because it's diagonal. A11, A22 is a principal submatrix, right? A11 is a principal submatrix of A with index I is only 1, right? So as I said, if the index is 1, right? What's the principal submatrix? That's A11, right? If index is 3 only, then that's a A33. Okay, the third diagonal element. So if this property is true, A is PSD, and any of the principal submatrix is PSD. Then if A is PSD, then all its diagonals are non-negative. So this gives you one way, right? If you see a matrix, its diagonal has negative values, you know it definitely will not be a PSD. Okay. So this gives us a very easy to check necessary condition, right? For PSD matrix, right? For PSD matrix. Then similar if, right? If you can partition your matrix like this, okay, and here A11, A22 are square, okay. Any partitions, okay, you can partition A11 can be any dimension, right? Then from this property, you can see, right, because A11, A22 obviously is a principal submatrix, right? A11 will be a principal submatrix if you choose the index say from 1 to here, right? Then its principal submatrix is A11. If you choose the index say it's from here to here, then his principal submatrix will be A22, right? So from here you can also see if for matrix you partition into a block, right? Into a blocks like this, A11, A22 are square. Then if A is PSD, if A is PSD, then A11, A22 are PSD, right? Also PSD, right? Any questions here? Obviously, you can check this is also true, but if it's PD, then its principal submatrix is also PD, right? So if A is PD, then will be positive. Its diagonal will be positive, right? This will be can be PD. Can be PD, right? Okay. And to show this property wise, it's actually quite easy because you just check its check the quadratic form. Okay. Just check the quadratic form. Right. If we consider this quadratic form, right, then this is true, right? For A is PSD, right? So this is our statement is that if A is PSD, then we have this, right? We have this. Now we want to check is AI, right? AI. We want to check the quadratic form of this. And of course, here I should use another notation. I use XI. Okay, so I want to check this. Right. Want to check this. Okay, so we have this quadratic form is non-negative for all x, right? And now we want to check for any xi is n-dimensional, then whether this quadratic form is not negative for this AI, because AI is n by n, right? Our index say I is has n elements, n indexes. Okay. Right. So from here, right, from here. So for all x, this is non-negative, right? For all possible x, this is now. So I restrict to the rows x. Restrict to those x. I call it the x tilde. Called x tilde, and x tilde is i's entry. Okay, will be 0. Okay, if I is not in the index I not belong to the index subset. Okay, so now we consider a subset of the x, right? We call it x tilde. This x tilde is that its entries element will be 0 if the index, if the location, right, of these elements does not belong to the capital I, the index subset. Then you see the quadratic form for A, for any x, right, is equal to, right, sorry, you consider this, the quadratic form of this. You know that this will be non-negative, right, for all x here. Because this is for all x, this will be non-negative. And this is only a subset of these x, right? Then of course it will be non-negative too, right? It will be non-negative, right? But you look at this, right? Here is will be summation I, summation j, right? Aij times x tilde I, x tilde j, right? And because xi or xj will be 0 if the I or j does not belong to the index set, capital I, right? So this is the same as this is the same as, right? We consider those ij that belong to the index I, right? Right. Then we define. Then we put this. Then we take out those non-zero elements of x tilde, right? How many non-zero elements x tilde? Only n elements, right? And put them out, and say it's xi, right? Then you see this is the same as summation I, summation j, right? Of this ai, ij, x, I. This is the same as this, right? This is the same as this. So what this xi is? This xi is we take the non-zero element from x tilde. Okay, this x tilde, right, is a large vector with m elements, and for those indexes that does not belong to this capital I, they are zeros. So then I take these non-zero elements, take out totally n of them, and take out n, put them into a new vector. The vector is xi. Then you can see this quadratic form is the same as this quadratic form. Okay, it's the same as this. Then this is xi, summation ai, xi. Okay. So then we get, because this is always non-negative, right? So this will be always non-negative, right? Because this is the same, and this is always non-negative. Okay. So we get this. We get this. Okay. So if you imagine that it's actually quite straightforward. Okay. It's actually quite straightforward. You look at this. Okay, and you consider that you put this element in X all to zeros if we index does not belong. Then you see its quadratic form is the same as this one. Okay, the same as this one. Any questions here? Okay, this okay. So the important consequence is that the most important two properties, as I say, you see the PSD matrix diagonal must be non-negative. Okay, and the block diagonals must also be PSD. Okay, because that's two most common seen cases. Okay. So the second property is to see his eigenvalues. We know that for Hermitian case, eigenvalue is real value. Then for PSD matrix, right? This is we'll see is okay. That lambda 1, lambda 2 to lambda n, the eigenvalues of a Hermitian matrix. Okay. A. Okay. Then if A, then A is PSD. Okay. If and only if lambda 1 to lambda n are non-negative. Okay. So this says that is A is PSD, then the equivalent condition is that you will see all its eigenvalues will be always an eigenvalue will be none. Okay. The diagonal being non-negative, that's only unnecessary. Okay, it's only unnecessary. Not a sufficient condition. But the eigenvalues or non-negative, this is if and only if condition. Okay, sufficient also necessary. If and only. Okay, so this is the equivalent. You check out matrix PSD, right? This gives you the way is you check its eigenvalue. Okay, if its eigenvalues are non-negative, then you see it's PSD. Similar, if it's PD, then this will be all eigenvalue will be strictly positive. Okay. So from here, of course, you see if it's PD, right, then it will be invertible, right? So a side product that A is PD, then implies A is also invertible. Okay, A is not singular. A is not singular. But invertible does not mean PD, right? So PD is invertible. PD is invertible. Okay, so how to show this? Right? We consider the eigenvalue decomposition. Because A is Hermitian, right? A is Hermitian, so always we can always have eigenvalue decomposition, and it's unitary diagonalizable, right? So we can write A equal to the V lambda V Hermitian, okay? V lambda V Hermitian. Here the V is unitary. And lambda is contained is diagonal. Eigenvalue. Okay. A is unitary. So you consider the quadratic form. Right? You consider it, check it quadratic form. Right? And you substitute this eigenvalue decomposition. So it's V lambda V Hermitian. Right? Right. So we get this. But if we define, if we let the Z, okay, as a new variable, which is V Hermitian X. Okay, so Z is like a rotated, right? V is a unitary, so it's doing the rotation. So Z is a rotated version of X. Okay, so X is non-zero, Z will be non-zero, right? Because just doing a rotation, right? So you see here can be written as Z Hermitian lambda Z. Right, and lambda is diagonal, so this is can be written as lambda I Z I squared. Okay. So from here you see, right? So first you see if lambda 1 to lambda m are non-negative, then from here you see, right? Because this is non-negative, right? And if lambda 1 to lambda n are non-negative, which means this is always non-negative, right? So you see. So you see A is PSD. Right. So from here you can easily see. So it proves that if lambda 1 to lambda n are non-negative, then A is PSD. Okay, the other direction is also easier to see from here, right? Because we see for all x, right? If A is PSD, second one, see if A is PSD, if A is PSD, which means that these will be non-negative for all possible x, right? And because x and z is 1-to-1, maybe it's just a rotation, right? So which means that if A is PSD, then this one, then this term will be non-negative for all z. For all z, right? Because this will be, if A is PSD, then this will be non-negative, right? For all x. So which means this will be non-negative, right? Because these are all equal. So this will be non-negative for all z as x and z is a 1-to-1 mapping, right? This is for all z. Right? If this is for all z, then you can choose. Also means this is also true. If you choose z has only one entry is non-zero, the others all are zeros, right? So then this gives us every lambda I or non-negative, right? For example, I choose z is only the first entry is non-zero, others are zero. And this quadratic form give you lambda 1 d1 squared, which is non-negative, which means lambda 1 is negative, right? So you see, means all the lambda 1 non-negative. All on. Okay. Any questions? Yeah. Right. Then this is very very important property. It's very important property. So obviously you can see, right, with this theory, you see A is PSD, right? And you can see that the determinant of A, what's the determinant of A? Right? Determinant of A is the determinant of V lambda, V Hermitian, right? It's a product of its eigenvalues, right? So determinant of A will be non-negative. And also the trace of A, which is a summation of these eigenvalues, will be non-negative. Right. And the last one I also mentioned is that A is PD. Then A is non-singular or invertible. Okay. So this also gives us some more properties, right? But determinant of a matrix is negative and definitely is not PSD, right? Or trace is negative, it's not. Okay, because you know that the PSD, all its eigenvalues should be negative. All its eigenvalues should be negative. Any questions here? It's not surprising, right? Not surprising. And where we will see this, the eigenvalues of a PSD matrix, where we will see in some simple case examples, actually you see the eigenvalues of PSD matrix give us a lot of insight. Ellipsoid, right? The 椭圆 ellipsoid, right? What is ellipsoid? In high school, right? In 2 dimensions. Right? In high school, William. How do we describe an ellipsoid? It's a x1, right? A1 square plus x2 a2 square, right? Less than equal to 0. We learn in high school, right? So this is how we write a ellipsoid. And A1, A2 basically describe the shape, right? I think this is A1 or A2, I forgot, or its inverse, okay? So A1, A2, you see determines the shape. Okay, how large the or it could be like a right this in the other direction, it could be like this, right, like a football. Okay. So you see this is written as let me here's a square root. Square root. Okay. This means this, right? If you put into a matrix, this is tell us this, right? In the two-dimensional case, right? In the two-dimensional. Is that right? Okay. So how do we describe a ellipsoid? If it is like this, then right. If in high school you see always is this standard ellipsoid. But how about this? How about this? Then for this one, right, you see it's rotated, right? It's rotated. Then by intuition is that if I change our coordinate, if I change our coordinate here, if I change my coordinate to new z1 and z2, then if I stand on this new coordinate, it becomes a standard ellipsoid, right? You see that? So this rotated ellipsoid is actually just as a rotation of the coordinate. Okay, so I change my coordinate, then I should see a standard ellipsoid, right? You see a standard ellipsoid. Okay, so you see that this is just a rotation of this coordinate. Rotation of this coordinate is change of coordinate, right? So in general, with this in mind, so you see in general we can define ellipsoid, okay, in this way, and extend it to high dimensional, more than 2 dimensions, right? The ellipsoid is a set of these points that satisfies here's let's restrict to real variables. Okay. The P is a PD matrix. Okay, so you can write it like this. It's X transpose P inverse X. Why this is ellipsoid? Right? Why is this is a ellipsoid? Right? Because it's PD matrix. You can have this eigenvalue decomposition, right? So that right called V lambda V permission, right? Because real value, so here can be orthogonal, can be permission, can be transpose. Okay. Okay, and this U is orthogonal. V is orthogonal. Right. So then you substitute this into here, then you see this quadratic, right, is X transpose. And it's inverse, right? What's the inverse of this? Its inverse is V lambda inverse V transpose. Okay. X. Okay. Then you see if we define a new random variable called Z, right? If here I define new random variable, define Z, which is V transpose X. Right. So you see here is actually this is what doing the change of the coordinate. So rotate your coordinate. Okay, rotate your coordinate. And for this new random variable, for this new variable z, it's like we rotate from this xy to here. Okay, so this we get z, and this exactly it's like this for two-dimensional case, right? So you see, this tells us the eigenvalues of this, right? This matrix P describe the shape of the ellipsoid, and his eigenmatrix V describe the rotation of an ellipsoid. Okay, so how this ellipsoid is rotated from the standard ellipsoid. Okay, from the standard coordinate. Okay, so you see, this indeed is an ellipsoid. Okay, it's just could be a rotated version of ellipsoid. Okay. So similar in statistics, we have this complex Gaussian distribution, multivariate Gaussian distribution. Right. You know, if we have if x, okay, it's a random vector, okay, and its elements follow this a Gaussian distribution. Okay, so it's multivariate Gaussian distribution. Okay, then his PDF probability and density function. Okay, probability and density function. Right, you know it's given by this. Like this. This is exponential. Exponential to the power of minus this quadratic form over 2. Okay. And here the mu is a mean or its average. The sigma is a covariance matrix. Okay. So mu is a mean, sigma is covariance. This multivariate Gaussian. Right. You know that if sigma, right, is a identity. If sigma is identity, then the Gaussian will be a very nice bell shape, like a bell shape, right? It's like a nice bell shape. So similar, you see the sigma, the covariance matrix, then tell you how this distribution, the PDF, is rotated and then it's stretched. Okay, so the eigenvector can do a change of coordinate, right? Eigenvalue and describe the shape of this Gaussian distribution. Okay. For example, in a two-dimensional case, this is a plane, two-dimensional. Then for standard Gaussian, if the covariance matrix is 1, 0, 0, 1, okay, with a identity, then this is a symmetric, right, completely symmetric bell shape PDF, like this, right? If it's still diagonal, Oh no, not diagonal. Okay, it's like this sigma. It's like this. But by intuition, then how well this PDF will like. Right from here, you see this correlation x1 and x2 has a positive number, which means that they are the first code x1, x2 they are proportionally they are positively correlated, which means if x1 become larger, then x2 are likely to become larger, right? So which means the bell shape will no longer be symmetric. Instead, it will be stretched and rotated. Will be like this. OK， 就想象一下这个3D 图啊，这个画是3D 图投影到2D 上。OK， 会 become 像一个一个什么那个海盗的帽子。OK， 就是这样啊。anyhow， 可能就是这样子，会沿着 x1 x2 对角轴会拉起来 ，right？ So you check this EVD, right? Check its EVD. Then actually this V tells you how this is rotated. This lambda tells you how it's straight. Okay, tells you how this is straight. Okay. Okay, so that's you see the physical meanings that can be given by understanding these eigenvalues for this symmetric PSD matrix. Okay. So the third property is that we can have, for PSD matrix, we can, similar to a scalar, right? For number, if it's non-negative, then you can have square root, right? If it's positive number, you can have square root. Then for PSD matrix, we can define square root. Okay, for PSD matrix, we can have square root. It's like a positive number, right? A non-negative number, you can have square root. So for Hermitian matrix, put this. So A is PSD, okay? If and only if, and this is very easy to check. Only if A can be written as B Hermitian B, okay? For some B belong to the matrix. B. Okay, B is not necessarily a square, okay? But for some matrix B. Okay, so then this B is called the square root of A, right? So this is like a 4, you can take a square root, which is 2. Okay, 2 times 2 equals 4. So this is like a B times B equals A. So B is like a square root, right? So this is easy to see, right? So this direction is quite easy. If A can be written like this, then this is like the correlation matrix, right? So if A can be written as B Hermitian B, right, then easily you can see the quadratic form is Bx, right? Bx 2 norm square. So will be non-negative for all x, right? So which means A is PSD. So this is quite easy. You see, can be, if a matrix can, it's like this, then it's of course it will be a PSD. Right. So the other direction, right? If A is PSD, then how can we show which can be factorized by this? We can by this eigenvalue decomposition, right? We can have eigenvalue decomposition. Second one, right? If A is PSD, then we have this eigenvalue decomposition, right? Well, eigenvalue decomposition, right? Right. And the A is PSD, so these lambda are non-negative, right? Eigenvalue are non-negative. Right? These lambda are non-negative. These lambda are non-negative, right? Of course, then we can have a square root, right? So we can have a square root for this lambda, right? Right. So we define this as use this notation, lambda, and I put a square root here. Okay, means this means we take a square root for the diagonal entries. Right. Right. So then you see this can be a B, right? You can define this as right. From here you can also see the square root is not unique, right? It's not unique because here I can in the middle, right? I can put in the middle. I can put any unitary matrix Q. QQ Hermitian. QQ Hermitian is identity, right? So I can put here, and then this gives a new B, right? So for the different Q, you can get different B. So you see this. This is not unique, right? It's not unique. Okay. Any questions? So this property we consider this. We study this property is for preparing for two applications. Yeah, because we'll see these properties were used in two quite famous applications. Okay, so it's good. Okay, the next property is this transformation, which says that if we have a Hermitian matrix A n by n and another B matrix which is n by n, okay, then for this we can construct a new matrix C, which is B Hermitian A B. Okay, so like it's like a sandwich. Okay. So C is obtained by, okay, you multiply in front of it and also after of A. Okay, both sides get this C. Okay, then there's some nice properties that can infer from the PSD of A or C to the PSD of C. Okay, so you say if A is PSD, okay, then this one should be easy to check to see A is PSD, then C will be PSD. Okay. But the other direction, if C is PSD, then A is PSD if and only if the B need to be full count rank. Okay, so PSD of A can infer PSD of C, but the other direction needs some condition on B. Okay, needs some condition. And the third one is if B is square and invertible, then the A is PSD if and only if C is PSD. Okay. So I will stop here. I will stop here. So with these two properties, then we on Wednesday we can see two quite famous example applications.